Hello everyone, it's our pleasure to present the paper Digital Twin Tracking Dataset, a new RGB+Depth 3D dataset for longer range object tracking applications. First, we will explain some background on 3D object tracking in augmented reality. 3D object tracking predicts the actual location of the object in real-world 3D space, even showing the object rotation and translation to its local coordinates. The 3D object tracking system aims to predict the 6 degrees of freedom rotation and translation of a target object using RGB image and LiDAR labs as multimodal inputs. By saying augmented reality, we are basically solving 3D object detection and tracking problems on small daily objects under indoor scenes. AR applications usually require not only object's location, but also their specific rotation and translation. Therefore, we also call 3D object tracking under AR scenario the 6 degrees of freedom object pose estimation. Current pose estimation methods are mostly data-driven, like dense fusion, FFB6D, ES6D, and also Uni6D, which means they need large-scale, high-quality data to train their deep learning methods. However, existing datasets like the YCB video and LIMO dataset, they have low-quality depth data and they are designed for short-distance robotics grasping tasks. In AR, the interaction distance will be much longer. With those limitations, we are thinking about why don't we build a dataset that is suitable for AR applications specifically. So here we will introduce our digital twin tracking dataset, namely DTTD. As mentioned before, our motivation is to build a new RGBD real-world 3D dataset for AR object tracking applications. We aim to provide data for data-driven object tracking methods in AR object tracking scenarios. The dataset is collected using cutting-edge time-of-flight sensor, Microsoft Azure Connect. And we also propose an accurate data collection and annotation pipeline based on OptiTrack, a professional motion capturing system to track the sensor locations accurately. We also include a wide range of distance and various lighting and occlusion conditions to diversify the distribution in the dataset. More details of the dataset, data generation, and annotation pipelines are made publicly available at the links shown in the slides. DTTD provides RGBD data using Microsoft Azure Connect TOF sensor for longer-range object pose estimation problems. Compared with other datasets, our DTTD dataset has longer average distance that is suitable for AR applications, and we are using TOF sensor to create higher quality data. We have 103 scenes in total under various occlusion and lighting conditions. This slide illustrates some of the data samples in DTTD dataset. DTTD dataset is collected under various real-world occlusion and lighting conditions. The first row shows scene images of 4 representative conditions. The second and third row show the corresponding semantic segmentation labels and 3D bounding boxes, respectively. DTTD depth data have the same resolution as the scene images. We also provide 10 texture 3D models, mostly daily objects. We also make sure the distribution of occurrence of objects is nearly uniform. Our data collection pipeline includes sensor synchronization between OptiTrack motion capture system and also Azure Connect sensor. We also ensure that the OptiTrack is properly tracking the coordinate frame of the camera sensor itself. Through these 2 steps, the pipeline is able to track long-duration, large transformation 3D motions while keeping precision of the pose labeling automatically. For annotation pipeline, we reproject RGB and depth maps into point cloud using camera intrinsic and the distortion coefficients in a 3D environment. We then let human annotators adjust the position and rotation of virtual models to obtain initial pose. After that, we perform some scene post refinement using ICP algorithm and generate corresponding post segmentation and bounding box labels. In this section, we evaluate selected state-of-the-art methods on DTTD to demonstrate its utility and usage. We provide in-depth analysis from both model level and dataset level perspectives to illustrate new challenges posed by DTTD. We evaluate dense fusion and dense fusion with ABC loss given ground truth segmentation masks without post-refinement process. We also provide evaluations on FFP60 with and without whole fielding algorithm applied. Notice that we didn't provide ground truth segmentation mask when training FFP60. We train the above methods on the training sets and report their performance on the test set. We follow the previous work to evaluate those methods on accuracy metrics, ADD and ADDS. These two metrics evaluate the distance of the model points between the ground truth posts and the predicted posts. The quantitative results on DTTD dataset are shown in this table. Dense fusion achieves average score of 84 ADDS AUC and 51 ADD AUC. Dense fusion with ABC loss has better performance over dense fusion on most of the objects. FFP60 achieves average score of 37 ADDS AUC and 14 ADD AUC. FFP60 without whole fielding algorithm has average scores of 26 ADDS AUC and 11 ADD AUC. Some qualitative results are shown in this slide. Given that we do not apply ground truth mask to train both methods in FFP60, we can observe some failure cases in FFP60's segmentation network. We suspect that FFP60 might have performed incorrect key point matching due to the complex background in scenes. Also, we observed that dark lighting conditions can make the FFP60 segmentation network harder to learn the detection of objects in a longer range. As shown in this table, with ground truth segmentation mask provided, the performance of dense fusion on DTTD is not comparable to that on YCP video dataset. We stipulate that DTTD poses the following additional challenges. First of all, compared to YCP video, objects captured in DTTD include longer distances on average with wider field of view. Therefore, it becomes challenging for the model to learn the object's low-level features, such as geometrical and appearance information. Secondly, DTTD provides more lighting variations than YCP video. The model also needs to bridge the gap of tracking 3D objects under varying lighting conditions. We believe the above performance differences make DTTD a better and more up-to-date dataset to demonstrate the technical gaps in AR 3D object tracking. In this section, we will show some potential usage of DTTD in AR 3D object tracking application. We will also discuss future versions of DTTD. Our dataset enables us to investigate more AR applications. One of them is AR shopping. This is a demo that we conduct 3D object tracking on a tomato can and overlay virtual labels. As you can see, when the user moves closer to the object, it shows the labels. When the user clicks on the object, more labels like video and nutrition facts show up. The labels can move with the object since we have its 3D rotation and translation. The demo depicts an exacting way of virtual shopping, and we would like to explore most possibilities of these applications in the future with DTTD. For continuous work, we also provide a new version of DTTD, which is captured using iPhone 14 Pro sensor for more realistic AR applications. In conclusion, we have introduced a novel 3D object tracking RGB dataset called Digital Twin Tracking Dataset to enable further research on extending potential solutions to longer-range object tracking problems. Future DTTD generations will adopt finer TOF sensors with diverse distances, objects, scenes, and backgrounds for household AR applications. Thank you so much for watching this video.